Howdy. So my name is Jackson Martin, and I've been working with Dr. Dimkovich over the summer on the development of nickel dissolution rates and hydrogen uptakes in various glycerol-based electrolytes. So although nickel is ubiquitous in the oil and gas industry, where it commonly encounters sour oil in the form of sulfuric acid contamination, our main motivation behind this project is on the potential discovery of nickel hydride formations. So for several decades now, spanning back to the early 60s, some like 60 years ago now, scientists and engineers have theorized that under cathodic polarization, nickel forms in nickel hydride due to electrochemical hydrogen charging. Unfortunately, the detection process has clearly been extremely difficult, in part due to the thermodynamically unstable nature of the molecule, if it even exists, right? So experimentation must be carried out in situ, which means on the sample surface, in an electrochemical cell, and one method of achieving this is going to be with neutron reflectometry. So that's pictured on the right. So NR shoots neutrons at the sample surface, and it has the potential to detect hydrogen without substrate degradation. So that's very uncommon. Think about using TEM, AFM, even SEM. All of these slowly degrade the sample. So having the potential to use something like NR, which doesn't do that on a nanofilm, is very crucial for testing, which, however, takes around an hour to finish. And this means that the sample can't completely corrode in that time period, right? So this requires us to optimize an electrolyte, which both maximizes hydrogen uptake, as shown on the right here, and minimizes nickel dissolution from, entirely happening. So unfortunately, this has to happen simultaneously, and these two are in direct contradiction with each other. So in order to find hydrogen concentration relative to different charging times, I prepared 50 micron thick nickel foils to charge in solutions containing a majority glycerol, either 8 or 10 volume percent borax, and 20 to 40 volume percent DI water. These electrolytes were started around 1000 RPM overnight, and this was done to develop a completely homogeneous solution, although it took a lot longer, admittedly, than I had first thought. So the foils were charged in these electrolytes for times ranging between 0 and 30 hours at a 600 millivolt overpotential using a 3-electrode cell setup with the sample as the working. So that's shown on the right here, where the counting electrode provides the hydrogen, which goes into the working electrode, which is the nickel foil. So after charging, samples were ultrasonicated in a mixture of water and acetone. They were weighed, and then they were melt extracted to determine the total hydrogen content in them relative to their respective mass. So the above graphs display the hydrogen concentration of nickel foils relative to various charging times and the electrolytes being used. So interestingly, the maximum absorption occurred around 10 hours in and either stabilized or began to decrease afterwards. So that's shown for the 52 vol, it began to peak around here. I could estimate that at 7 hours. And for the 70 vol electrolyte, it began to peak around the 10-hour region. So as I mentioned before, interestingly in the 52 vol, it began to almost exponentially decrease after the 20-hour area, and there is a slight decrease in the 70 volume percent glycerol as well. So this maximum concentration was significantly higher using the lower volume percent glycerol, and this seems to indicate that its higher viscosity may slow the diffusion of hydrogen as its output throughout the solution. So previous work has been done charging nickel with a water and sulfuric acid-based electrolyte, which actually experienced lower hydrogen concentrations than either of the two glycerol borax-based solutions being shown. So this indicates either solution would support the formation of a nickel hydride through proper hydrogen adsorption, which is really great news because that's what we're shooting for with these experiments. So in order for us to mimic future NR experimentation, nickel dissolution rates had to be found using fabricated thin films. This was performed using electron beam evaporation on silicon wafers at AggiFab to deposit approximately 500 nanometers of nickel evenly across the substrate surface. Charging of these took place on the nickel surface using a bottom-mount electrode as shown on the bottom left to charge only the thin film and none of the silicon acting below it. So then profilometry was used to characterize any changes in roughness indicating local corrosion pitting. It was also used to perform line scans of regions before and after charging to look for general corrosion, as seen here, where it begins dragging along the nickel surface, drops down to the silicon wafer, and comes back up to the nickel. So hopefully we'll be able to see a change before and after charging. This is what could be used to find the dissolution rate of nickel in each electrolyte. So pitting was actually confirmed by comparing surface roughness before and after charging, and after only 1 hour charging in a 70 volume percent glycerol-based electrolyte, there was a 10x roughness increase. So that's going from an average roughness of 0.0216 microns to 0.2629 microns, which is actually over a 10x increase. Additionally, we can look qualitatively at the SEM photos on the right to see that pitting dramatically increased with charging time from 1 to 5 hours. Also, it is important to note the change in thickness of the uncharged nickel surface shown on the left. So the difference in surface height here between the blue and red region is nearly 1,000 nanometers. So unfortunately, this does show us that the E-beam wasn't great at evenly distributing the nickel after all. And instead of being 500 nanometers, like it probably is here, it's over a micron here likely. So unfortunately, general corrosion was a lot trickier to analyze because it didn't occur uniformly over the sample. The graph on the left shows 2 line scans done with the profilometer before and after charging, and the rate of nickel dissolution was entirely dependent on location relative to the center. So the general corrosion exponentially increased further towards the middle of the charged part of the sample. I used the highest loss of thickness in an effort to try to give a quasi-conservative estimate of nickel dissolution. It is also worth noting that this measurement wasn't done with the 52 volume percent electrolyte, since it completely degraded at least 10 minutes in, probably around 8 minutes. And this was just a completely insufficient charging time for nuclear reflectometry in the future. But using the 72 volume percent electrolyte, it had an approximate dissolution rate of negative 0.225 nanometers per second, which on first look actually sounds pretty good. I mean, 1 nanometer every 5 seconds isn't too bad, right? But since experimentation with NR would take around an hour, and this is using around a 100 nanometer film, both of these are kind of loose, but the ideal electrolyte would have a rate of negative 0.027 nanometers per second. So that's nearly 10 times smaller. And there's a lot of work to be done in reducing this general corrosion. But increasing the glycerol concentration in the electrolyte, at least for now, it appears to have the potential to work and to further decrease this to the point to where we can actually do the experiment. So circling all the way back to the main motivation behind this project, I've found that charging nickel in every glycerol-based electrolyte exceeds the necessary level of hydrogen adsorption needed for experimentation with NR. Unfortunately, this does come with the cost that they cause far higher dissolution rates than we can currently work with. So going forward, we have a proposal which we'll be doing the next month on August 28th, and further optimization is clearly necessary for these electrolytes. More research will be conducted with higher concentrations of glycerol to further mitigate nickel corrosion. Hopefully, additionally, other methods of thickness characterization may hopefully present themselves to speed up our ability to find nanofilm thickness. This research has definitely challenged me in ways I hadn't expected, but I'm very excited for the future of where this project is going and to hopefully confirm or deny the presence of nickel hydride formations in the coming months. So thank you for watching.